Okay, in this example, we have an implicit relation in front of us, and for the first time, getting y by itself looks like it's going to be a bit of a chore. And we will do that. We're going to isolate y. It is possible in this case, but it's pretty time consuming, and the derivative is not really that pleasant either. And you'll see that implicit differentiation is much more efficient in this situation. So we're still going to stick to our rules of differentiation that we've used so far in this course, at least one last time. And we'll try to get y by itself. So we have 4x squared. Now since I have a y squared and I have a 6y, a minus 6y term, the way we can get y by itself is to isolate, at least concentrate on these y terms here and try to make a perfect square, and of course balance our equation at the same time. So to make a perfect square, you take half of your linear term there, half of minus 6, and you square it. So if I take half of minus 6, I get minus 3, and I square that, I get a plus 9. Now I didn't have to factor anything out. There's a plus 1 in front of that bracket, so all I got to do is add 9 to both sides of this equation. And if it's not really obvious why I did that, well, I think it might be after we factor that trinomial that I just created. If we try to factor y squared minus 6y plus 9, you'll see that it's a pair of factors that are identical. It's y minus 3 times y minus 3, or a perfect square, which was the point, to completing the square. So, and we also get, of course, 7 plus 9 on the right-hand side. So now we can isolate our y minus 3 squared term and use square roots and eventually get y by itself. And again, keep in mind, this is not the most efficient way of doing this question. It's just a really good illustration and I guess a comparison that implicit differentiation is going to be much more efficient. So let's get our y minus 3 squared term isolated. So we'll subtract 4x squared from both sides. And now we can use our square root principle, y minus 3. Remember, since that's an even power, we have to introduce a plus or minus root here. Square root of 16 minus 4x squared. And lastly, at least with isolating our y variable, it's going to be plus 3. Add 3 to both sides. And then, of course, plus or minus root. As you can see here, this is not a function we're dealing with. Most of the time when we input an x value into this expression, we're going to get 3 plus or minus some number, and we're going to get a pair of outputs. Of course, that's not how a mathematical function works, which is why I was referring to this as a relation the whole time. And we'll check the graph out in a little bit, but for now, we'll worry about differentiating this. We did manage to get y by itself, and even though that plus or minus is in there, I'm just going to kind of sidestep that and just not worry about it a whole lot, and we'll just go ahead and differentiate this and really just see it as a sum or a difference in this relation here that we're differentiating. So if we have y prime, I'm going to basically take the derivative of the right hand side, of course. So the derivative of 3 is going to be 0, and then I'll sidestep that plus or minus, and we'll differentiate the square root of 16 minus 4x squared. So that's a little bit more familiar. So all I really did there was differentiate that sum, I will call it, even though there is a plus or a minus in the middle there. And the derivative of 3 is 0, which is there's no need writing anymore, and I'll just make sure I copy that plus or minus down. And then to differentiate, before we go ahead with that derivative, of course, we will write this as a power. So 16 minus 4x squared, we'll write that as a power of a half. And then we can differentiate that with our chain rule. So we have a plus or minus. Now we can go ahead and finally differentiate this. Our power function gets differentiated first. And we have our trapped 16 minus 4x squared. Subtract 1 from our power of a half. We get negative a half. And don't forget to finish off with your chain rule here by taking the derivative of the inside, which is going to be minus 8x. We're getting close to finishing off our derivative here, so we can clean this up a little bit. So we can take half of 8 and get minus 4. So I'm going to call that minus 4x. I guess I better write that plus or minus. We'll deal with that in another second. So right now we got minus 4x in the numerator. And I'm taking that negative power below, and I'm going to switch that power of a half directly back to a root, of course. Since we started with roots, we might as well go back to them. Okay, and that plus or minus is in a weird spot, so actually let's move it one more time. I'm going to move that to the denominator. If you're wondering why I'm doing that and not trying to multiply, I guess, that negative by the plus or minus, well, there's a madness to my ways here. You'll see in a few more seconds. So that plus or minus, if it goes to the bottom, I guess I'll write that all in pink. It's going to be 16 minus 4 x there. I should say the square root of 16 minus 4x squared, plus or minus. And hopefully you can remember that we've seen that before. It is up here. What was plus or minus 16 minus 4x squared? Well, we don't have it exactly. But I guess we could look right here. We have, actually we do have it exactly. It's sitting right here. We have y minus 3 is equal to plus or minus the square root of 16 minus 4x squared. So in our denominator down below in pink, actually we just have y minus 3. So we're going to rewrite that derivative one more time. So we'll just say the derivative that we found through kind of terrible means here is going to be minus 4x and y minus 3 in the denominator. Now, of course, that last step I did there was to set us up for implicit differentiation, because when we do implicit differentiation, which I think you'll see is a whole lot less time-consuming than the way we did this by writing it as an explicit relation first, this will allow us to compare our implicit differentiation result. Okay, so let's differentiate this relation using implicit differentiation. So, of course, we're going to take the derivative of the left and the right-hand side of this equation. And since everything is added and subtracted on the left-hand side, we just go ahead and got a lot of differential operators to write in, but I'll write the first one in with you. We got the derivative of 4x squared, and then I'll just write down the rest here quickly. Okay, so we got all our differential operators introduced there. We got 5 different derivatives, so let's start on the very left. The first one is easy. We're differentiating 4x squared with respect to x. So that is going to be just 8x. Our second derivative, we're differentiating y squared. So here's where we have to be aware that y is dependent upon x. I'm going to call it a function of x, but remember, y is really 2 functions of x fused together in this kind of weird relation that we're dealing with, but it doesn't really change how we're going to approach our derivative. I'm just going to simply say that I have to differentiate something that's dependent upon x squared. If you want to just think of it as a function, that's good enough, but remember it's the plus or minus has fused a pair of functions together. So we have to differentiate that probably in the next step with our chain rule. And then we'll move on here. I think I'm going to extract that coefficient. I can put that in front of our derivative. So technically I did something there. And then just remind ourselves that we're dealing with y of x. Y is a function of x. So we have to differentiate that as well. And then, of course, everything else is finished. We got a derivative that's 0, and we got another derivative that's 0 on the right-hand side. So I guess we can introduce a set of brackets there and there. For some reason that's helpful. That last pair, probably not. So we're getting somewhere. We have an 8x, derivative of that first term. And now, of course, since we have a y of x trapped inside of a square, we have to deal with our chain rule and differentiate the power first. So the 2 comes down in front. Our y of x is still trapped. You can think of it as a function if you wish. And that's going to go to a power of 1, but I can see that maybe looking too much like a prime, so I'm going to leave that off. And then to finish off our chain rule, we're going to have the derivative of y of x, which is y prime of x. And then we have minus 6, sidestepping that coefficient and the derivative of y of x. Yes, we just kind of did that. The derivative of y of x is y prime of x, and this equals 0. So you might not be a big fan of that the first time through. It's a little difficult because, of course, you have a chain rule application there, and you also have just a little bit of sidestepping of a coefficient. But we have a pair of y primes, and that's what we're looking for. So now we're going to isolate those y primes on one side of this equation and clean up this mess, and we'll have our derivative. Okay, so we'll... and I think at this point we can drop our y of x stuff as well, but maybe we'll save that for one more step. Let's just rewrite this in a verbatim here. We can see that there's a y prime there, so of course we want to leave that on the left-hand side. And we got 6 y primes. So all I'm really going to do is subtract 8x from both sides, and move that 8x term over to the right-hand side. Now, if you're wondering how you're going to get y prime of x by itself, of course, that's just a common factor that we can pull out of that difference that we have. There's a y prime of x in both of those. So maybe just open up another set of brackets here, so you can see that. And this equals minus 8x. So if I pull out that common factor, I'm going to be left with a 2 multiplied by, I guess I'll leave those squares so you can see that, square brackets. If I pull out that y prime in the first term, I'm left with 2 times y of x, and then over here I just have a minus 6. So now we just have to divide everything, this whole equation, by what you see in the purple brackets there, and we'll have our derivative. This is going to be y prime of x. Make sure that looks like a prime. Y prime of x equals minus 8x all over 2 times, and I'll write those square brackets one last time, it's kind of awkward, divided by 2 times y of x minus 6. So let's get rid of all those extra brackets and get rid of the of x function notation that served its purpose. We don't need that anymore, and we have y prime, you can think of x, got a minus 8x on the top, and I have 2 times y minus 6 on the bottom. Now that's not exactly what we had before, but of course you can see there's a common factor of 2 there, so I can divide everything by 2 and do one more rewrite, maybe just alongside it here. If I divide the top by 2, I get minus 4x, and if I divide 2y by 2, I get y, and lastly minus 6 by 2, I get minus 3. In Eureka, we have our derivative that matches exactly the first derivative. Now, believe it or not, that implicit differentiation is a lot more efficient once you get the hang of it, and you're probably not there yet, but we're only on example 2, so stick with it. You'll see in the next example that getting y by itself can be even more miserable than this example, so we might be kind of at the crossroads. I'm not sure if implicit differentiation is a lot easier than the explicit way that I did it initially, but like I say, you're going to run out of options in the next example or 2. I almost forgot to show you the graph of this function, and here it is in front of you, and this is called an ellipse. And something we'll consider in a next video is, how do I find the slope of a curve such as this? And I want you to think about that a little bit now. We'll address this in future videos, but as a little bit of a hint, of course, that's an x and a y value that you have, and your derivative is, if you found it via implicit differentiation, it's typically going to want the x and the y value of your point of tangency. And if you input that rather awkward set of coordinates, you can find the slope of your curve. And like I say, we'll explore that a little deeper in subsequent videos.